how do we take the derivative of this function here? Notice how it's not like the other ones we've done. It's not just a simple polynomial. We can't use the product rule. We can't use the quotient rule. Instead, we can look at this function as it's sort of like a function within a function. We have this square root function here, and then we have this x squared plus 5. So how do we take the derivative of a function inside a function? And the trick is to take a substitution, or make a substitution. So we can say y equals root x squared plus 5. What's the substitution that makes sense here? Well, wouldn't it make sense to put the stuff inside the square root as another variable? So let's make u equal to x squared plus 5. That simplifies it a bit, right? Because now if we rewrite this, it's going to look like this, the square root of u. Can we take the derivative of this function now? Yeah, no problem, right? So remember, the square root is just u to the power of 1/2, right? So let me just write that here. So y also equals u to the power of 1/2. Take the derivative. So I'm going to call this derivative dy by, should we call it dy by dx? Well, if we look, we're not taking the derivative in terms of x anymore, right? Our variable is now u. So we should write this Leibniz notation as dy by du. So the derivative of y with u as the variable. And this becomes 1/2 u to the negative 1/2. Okay? There we go. We took the derivative of it. Are we done? What did we actually find here? We found dy by du, so the derivative of y with respect to u. But is that what we actually wanted in the question? The question asked us to find the derivative of this. So essentially, the question asked us to find dy by dx. But we didn't find dy by dx, we found dy by du. So the question is, if I want dy by dx, I started off by finding dy by du. How can I then get dy by dx? Well, the key is we now must use what's called the chain rule. And the chain rule is listed right below here, as you can see. And the chain rule says dy by dx, so the derivative of y with respect to x, is equal to dy by du, which we found, times du by dx. So that means we need to find, if you think about what this means, we need to find the derivative of u with respect to x and multiply those two derivatives. So looking back up here, essentially that's what we need to do. We need to multiply this by du by dx. And if you want to think about this as sort of as a pattern here, we can see that if you treat these as fractions, sort of like dy divided by du, du divided by dx, what happens to those fractions? Well, what would happen is that these two du's would sort of cancel out, and then you're left with dy by dx. Now, these things aren't actually fractions, right? They're just telling you that you're taking the derivative of y and the derivative of u. But just as a way to remember how the chain rule works, you can always remember, you can just sort of cancel those out, and then you're left with dy by dx. Okay? All right, so let's go back to our question. So we have dy by du, we have u, and remember what we needed. We needed du by dx. Well, how do we find that? That's just the derivative of u with respect to x. And we can do that, it's just the derivative of this thing. The derivative of that is just 2x. So essentially, coming back over here, let's just plug in what we know now. So we know dy by dx, let me just zoom in here, dy by dx is equal to 1/2 u to the negative 1/2, which is the derivative of y with respect to u, times du by dx, which was just 2x. So there's our derivative. What's wrong about this derivative? Well, if we'd like to get everything in terms of x, can't we just plug our u back in as x? And we can do that. So our u was just x squared plus 5, so this is just going to be x squared plus 5 to the negative 1/2 times 2x. There you go. Now it's all in terms of x, and we've found our derivative. We can also simplify this a little bit more, so I'm just going to put this. We can see that this 2 and this 2 are going to cancel out with each other. This big thing in the brackets is going to end up in the denominator because it's got a negative exponent. So to simplify, it should look like this. X over, just move down there, x squared plus 5, and sort of like the root of that whole thing. So that's dy by dx. So this is the chain rule that we use to evaluate problems like this. And the chain rule, very powerful because it allows us to basically break down a derivative into its separate parts when you have a function within a function. Okay, so just remember this is the chain rule, and that's what we're going to use to solve the rest of these questions. So how do we differentiate this? Again, we have a function within a function. It's like x plus 4 is one function, and then that whole thing to the power of 7 is sort of your outside function. So the obvious substitution to make here would be let u equals x plus 4. And if that's the case, y is just equal to u to the power of 7. Right? So now we want to take the derivative. So what the derivative is, keep in mind, dy by dx, which is what we're trying to find, is just going to equal dy by du, so the in-between function, times du by dx. So we just need to find those two things, dy by du and du by dx. So going back up here, we can find dy by du is just equal 7u to the 6th, okay? And du by dx is just the derivative of this thing, x plus 4, which is just 1, right? The derivative of x is just 1. So plugging it back into the chain rule, we see that this is just 7u to the 6th times 1. Or if we want to make everything in terms of x again, we can plug in that u is just equal to x plus 4 to the power of 6 times 1, which is just going to go away. So there's our final answer for dy by dx. Next question. Let's rewrite this function 1 over 2x plus or minus 3 to the power of 4. Let's rewrite that all in the numerator. So y equals 2x minus 3, and to put them in the numerator, we're going to make the exponent negative 4. And let's basically do the same thing we did in the last question. So I'm going to make u equals to what's in that brackets, 2x minus 3. So y is going to equal u to the power of negative 4. Again, I'm going to write out my chain rule. So dy by dx is equal to dy by du times du by dx. Okay, so we can find dy by dx is equal to negative 4u to the negative 5, and then du by dx, oh sorry, I made a mistake here. This should be dy by du, right? Because there's no x in that we're taking the derivative of. So it's u, the variable that we're taking the derivative of. Okay, so sorry, going back, du by dx is equal to 2. So the derivative of this whole thing, dy by dx, is just going to be negative 4u to the negative 5 all times 2. Again, simplifying there, we get dy by dx is equal to, well, that negative 4 and that 2 are going to multiply. So we're going to get negative 8, and then that u to the negative 5 is going to go to the denominator as u to the 5th. And then again, to make it in terms of x, I'm just going to replace that u, negative 8 over, and what was u again? Need to go back up here. U was just 2x minus 3, right? So we'd end up with 2x minus 3 all to the power of 5. There we go. There's our derivative. Now we have example C, which looks a little bit more complicated, but what I would recommend, if you're feeling comfortable with what we've done so far, pause the video here, try this one yourself before actually seeing the solution. So the solution, there's an obvious substitution to make here. This big ugly thing in the brackets to the power of 10, right? So this big ugly thing in the brackets, do we know how to find the derivative of that by itself? And the answer should be yes. We can use the quotient rule to evaluate this, right? So when we're able to evaluate that, that's a good hint that we should use that as our substitution. So u equals 1 plus x squared over 1 minus x squared. So that makes g of x just equal to u to the power of 10, right? We know with our chain rule, we're going to need to find dy by dx is just going to be dy by du times du by dx. And so notice here, we don't actually have a function called y, right? It's called g of x. But another way of thinking of dy by du, remember that just means the derivative with respect to u, right? So another way of thinking of g of x is going to be g prime, instead of x, g prime of u. It's the derivative of g with respect to u. So we can just use that notation, or if you want, you can just call it y and use the other notation. But the derivative of this is 10u to the power of 9, right? U, on the other hand, we can use that du by dx. And again, we can use, well, it's something over something else, so that should trigger the quotient rule in your head, right? So the way we do that, once again, is we take the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So I'm just going to do this super fast. The derivative of the top is just 2x times the bottom, 1 minus x squared. Try to fit it all on one line here. Minus the derivative of the bottom, or sorry, the top times the derivative of the bottom. So 1 plus x squared, and I will have to move it over a little bit here, times the derivative of the bottom, which is negative 2x, all over the bottom squared. 1 minus x squared, all squared. Okay, that's not that pretty. Does it really matter though? Well, let's try plugging it in to our equation here. So dy by dx is dy by du, or, as we set up here, g prime of u, which is just going to be 10u to the power of 9, times du by dx, which again was 2x, 1 minus x squared, minus 1 plus x squared times negative 2x, all over 1 minus x squared squared. And then we like to make everything in terms of x, just because when we plug in numbers it makes it a little bit easier. So remember, our x was 1 plus x squared all over 1 minus x squared to the power of 9 times 2x, 1 minus x squared minus 1 plus x squared times negative 2x, all over 1 minus x squared squared. Okay, not the prettiest derivative, but if we wanted to plug in a number for x there, it wouldn't be that difficult. That'd just be a lot of calculator work to find the slope of the tangent of that function. Before we go on to the next example, I just want to draw your attention to something here. There's a bit of a pattern that appears when we take the derivative of things like that, where we have a function and it's to a power, for example here, like 10. What does our answer come out to? Can you see, by looking at our answer, can you see where the power rule is? So we had a 10 here, right? It's sort of like we brought the 10 down here and we reduced it to a value of 9, right? So it's like we applied the power rule to the function. What's inside here hasn't changed. It's what was here at the beginning. And what's at the end here? It's just the derivative of what was inside. So there is a pattern here that we can use to sort of make a shortcut for questions like this. And let me show you what that shortcut is now. So looking here, I just wrote down on the side of the page, I wrote down another example. Looking at the pattern we just saw, it's like we can apply the power rule to this whole function as long as we multiply by the derivative of what's inside this bracket. And we call this the power of a function rule. So I'm going to apply the power rule to this function. So I'm going to bring down, so f prime of x, just going to bring down that 4 in front, 4, 3x squared plus 5, and that 4 becomes a 3. But we're not allowed to just apply the power of the function, the power rule to this function without then multiplying by the derivative of what's inside the brackets. So the derivative of what's inside the brackets, 3x squared plus 5, is just going to be 6x. So when we have a simple problem like this, where it's just a function raised to a power, you don't actually have to apply the chain rule. We know this basically is the chain rule, right? This is dy by du if we call this u, and this is just the derivative of u. But we don't actually have to apply the chain rule. We can just do this pattern, okay? And we call this, once again, we call it the power of a function rule. Okay, and this will be very handy. It'll save us a lot of time. And really what it is, if we want f prime of x, we're going to take f prime of u, whatever u is, so some inside function, times the derivative of u. Right? And that's exactly what we did here. We just found the derivative of the outside function, which is like saying sort of u to the power of 4, and we took the derivative of that, leaving what's inside the brackets the same, and then multiplying by the derivative of what's inside the brackets at the end. Okay? So let's see how we can apply that rule to this problem. We have a problem like this where we know we're going to have to apply the quotient rule. So I'm going to call that the top part A, the bottom part B, in which case f prime of x we know is just going to be a prime b minus ab prime all over b squared. Okay, so the question is here, what is a prime? What is the derivative of a? 2x plus 5 all squared. So I'm going to do that part off to the side. So if I call a as 2x plus 5 to the power of 2, let's apply our power of a function rule to find out what a prime is. So remember, our power of a function rule is sort of like the power rule, but we have to multiply by the derivative. So again, we're going to bring that 2 down in front, 2x plus 5, and then we have to multiply by the derivative of what's in that brackets, the derivative of what's in here, which is just going to be 2. So a prime really is just 4 2x plus 5. Okay? So now that we know what a prime is, we can just plug everything into our equation. So a prime is just 4 times 2x plus 5 times b, which is 3x plus 1. And I'm going to run out of space here, so I'm just actually going to erase this. I think you guys understand that part. Bye-bye. Minus ab prime, so a is 2x plus 5 squared. B prime is just going to be 3, right? All over b squared. 3x plus 1 squared. There you go. That's what f prime of x is. So when you use the power of a function rule, you don't actually have to make that substitution or use the chain rule, even though that's what you're doing, sort of behind the scenes. Okay? And then we have this one. We can see that the power of a function rule is going to be really handy here because we have two functions that are raised to a power. So let's start off by calling this a and this b. And then we see that h prime of x is just going to be a prime b plus ab prime. So we basically need to find out what a prime and b prime are. So again, I'm going to do that off to the side. So if a is x squared plus 3 all to the power of 4, we take the derivative of that using the power of a function rule. So a prime is just, the 4 comes down in front, 4 x squared plus 3 to the power of 3, and then we multiply by the derivative of what's in the brackets, which is just 2x. There we go, that's a prime. And we can actually simplify, why don't we simplify that just to make it a little bit easier to write down. So 8x x squared plus 3 to the power of 3. Okay, and then we have b, which is 4x minus 5, all to the power of 3. B prime is just going to be 3 times 4x minus 5 to the power of 2 times 4. And just rewriting that, 12 4x minus 5 squared. Okay? So now that we know all those things, we can plug it into our product rule. Again, I'm going to run out of space here, but that's okay. So a prime is 8x x squared plus 3 cubed. B is 4x minus 5 cubed. Okay, you know what? I'm going to stop it here, pause it here, finish the question, and what I'm going to do is I'm going to show you the answer in a second. So pause here, try it yourself, and then unpause when you're ready. So there we go. That's the final answer of h prime of x. One thing to keep in mind, there's going to be more than one way to answer a lot of these questions. Sometimes you can use the chain rule or the quotient rule or the product rule, and it's just up to you whichever you think whichever path you think is the easiest. As long as you make it super clear in your process what you're doing.